Welcome to the deep dive. Today, our mission is to really get into the physics of fluids. We want to make sense of these invisible forces all around us.
Right. We're talking pressure, buoyancy, how things lift and float.
And we're using a great instructional summary as our guide here. It really breaks things down.
It does. It's very clear, designed for instruction, and it specifically gives a nod to physics teacher Hakaveli Torun for his contributions. A solid base for us.
Absolutely. So we're asking, why do ships float? How can fish just hang out in the water? And, how does that hydraulic lift actually hoist up a car?
It all starts with pressure.
Yeah.
Hashtag tag fluid pressure, the invisible foundation.
Okay, pressure. Now, instinctively, I think of gravity just pulling water downwards, but the first kind of surprising thing here is that fluid pressure pushes in all directions, doesn't it?
Exactly. Equally. Up, down, sideways.
Yeah.
Everywhere within the fluid, it's force per area acting on any surface submerged in it.
So what determines how much pressure there is at any given point?
Well, that's where it gets interesting.
Yeah.
It boils down to just two things, really. The fluid's weight density, basically how heavy it is for its size and depth, how far down you are.
Wait, so the amount of water doesn't matter, like a thin, deep tube versus a wide, shallow lake?
Nope. If you're at the same depth, in the same liquid, the pressure is identical. The shape or total volume of the container, irrelevant for the pressure at that specific point.
Huh. So the formula is just pressure, weight density times depth.
That's the core of it, yes. Simple, but powerful.
But there's another layer, isn't there? We're forgetting something pressing down on everything.
Atmospheric pressure. You live at the bottom of an ocean of air, right? So for the total pressure on something underwater,
Yeah.
you absolutely have to add the air pressure pushing down on the surface.
Right. Okay. That makes sense.
And this whole depth-pressure relationship has some amazing real-world consequences. Think about giraffes, for instance. Shekel 13.3 in the notes shows this.
Giraffes, how do they fit in?
Well, imagine a giraffe lowering its head maybe, 15, 20 feet to drink water. The pressure difference on its brain between standing tall and drinking is huge because of that change in depth relative to its heart.
Oh, wow. Yeah, that must be an enormous pressure swing. Enough to cause serious problems, you'd think. Fainting or worse.
It would be, but they have adapted. They have these incredibly thick elastic veins, especially in their neck. These act like pressure regulators, handling those massive swings as they lift and lower their heads. It's biology solving a physics problem.
That's incredible. A living example of managing pressure due to depth.
Definitely.
And, this wasn't lost on ancient engineers either, was it? Like the Romans with their aqueducts. They must have understood these principles to get water flowing over long distances.
Oh, absolutely. They might not have had the exact formulas, but they had a practical mastery of how water pressure worked based on height differences, essential for their infrastructure. Hashtag buoyancy and the mastery of density.
Okay, so pressure pushes in all directions, and it increases with depth. And that leads directly to the next big idea. Buoyancy, right? The upward push.
Precisely. Pressure difference between the bottom and top of a submerged object creates an overall upward force. That's buoyancy. And for the definitive take on that, we look to Archimedes.
Archimedes, around the 3rd century BC, yeah. What's his principal state?
It's actually beautifully simple. Archimedes' principle says the buoyant force on an object is equal to the weight of the fluid it displaces.
Okay, say that again slowly. Equal to the weight of the fluid it pushes aside.
Exactly. Not the object's weight, but the weight of the water or whatever fluid that had to move out of the way to make room for the object.
So what determines how strong that buoyant force is?
Two things then. One, the density of the fluid itself. Denser fluids push up harder. Think saltwater versus freshwater.
Right.
And two, the volume of fluid displaced, which naturally is the same as the volume of the object that's actually under the fluid surface.
Crucially, it's not about how heavy the object itself is or what it's made of, just how much space it takes up underwater and what fluid it's in.
Correct. 10 kilos of lead and 10 kilos of styrofoam, if they somehow had the same submerged volume, would experience the exact same buoyant force.
That's a key distinction. And that directly explains why things sink or float, doesn't it? It's a comparison. Hashtag why things sink or float.
It's all about density comparison. 3 scenarios.
Okay, lay them out for us.
1. Sinking. If the object is denser than the fluid, its weight is greater than the maximum buoyant force possible when it's fully submerged. So down it goes.
Makes sense. Heavy stuff sinks.
2. Floating. If the object's overall density is less than the fluid's density, it sinks only until the weight of the fluid it displaces exactly equals its own weight. Part of it stays above the surface.
Like wood on water.
Exactly. And 3. Suspended. This happens when the object's density is exactly the same as the fluid's density. It stays fully submerged, but doesn't sink or rise. It just hangs there, neutrally buoyant.
That suspended state, that sounds like what fish are doing, right? They seem to just hover effortlessly. How do they manage that? Like Shekel 13.15 suggests.
Ah, yes, fish are masters of buoyancy. They use their swim bladders. It's essentially an internal balloon they can inflate or deflate.
So they change their volume.
Precisely. By adjusting the gas in the swim bladder, they change their overall average density. More gas, lower average density, they rise. Less gas, higher average density, they sink. Or they find that sweet spot to just stay put without wasting energy swimming.
That's really neat. Okay, so that brings us to the classic question. The giant steel ship.
Yeah.
A 10,000-ton ship. Steel is way denser than water. Why doesn't it sink like a stone?
It comes back to that average density idea we just talked about with floating. Yes, the steel itself is dense. But a ship isn't a solid block of steel, is it?
No, it's mostly hollow inside. Full of air.
Right. And air is incredibly not dense. So engineers designed the ship's hull to enclose a massive volume. When you calculate the density of the entire structure, the steel plus all the air inside that average density is much, much less than the density of water.
So the ship as a whole system is less dense than water, even though its main component, steel, isn't.
Exactly. To float, it needs to displace a weight of water equal to its own weight, 10,000 tons in your example.
Yeah.
And to displace that much water, you need a huge submerged volume. The hollow structure provides that volume while keeping the average density low. It's clever design. Hashtag leveraging fluids, Pascal's principle.
Okay, so we understand pressure, we get buoyancy. Now, how do we actually use fluids to do work, like mechanically? That takes us to Pascal, right?
Yes, Blaise Pascal and his principle. This is the key to hydraulics. It's about how pressure behaves in a contained fluid.
And what did Pascal figure out?
He stated that if you apply pressure to an enclosed fluid, one that can't be compressed easily, like most liquids, that pressure is transmitted undiminished to every single part of the fluid and also to the walls of the container.
Undiminished. So if I press down with a certain pressure on one part of a sealed water system,
that exact same pressure instantly shows up everywhere else in the system.
okay, that seems simple enough, but how does that help us lift heavy things?
Because pressure is force divided by area. Since the pressure is the same everywhere, if you have pistons of different areas in your contained fluid system, the forces on those pistons will be different.
Oh, so you can multiply force.
Precisely. Imagine a system with two pistons connected by fluid, a small piston with area A1 and a big one with area A2. If you push down on the small piston with a small force F1,
It creates a pressure, P equals F1 over A1.
right, and that same pressure P acts on the large piston. So the upward force F2 on the large piston is P times A2, which means F2 is F1 times A2 divided by A1.
So if the large piston area A2 is, say, 50 times bigger than the small one, A1, like in the example, Shekel 13.22.
Then the output force is 50 times the input force.
Yeah.
A 10-kilogram weight on the small side could lift a 500-kilogram weight on the large side. Huge mechanical advantage.
That's incredible. What's the catch? There's always a catch.
Well, you trade force for distance. To lift that 500-kilogram weight just 1 centimeter, you'd have to push the 10-kilogram weight down 50 centimeters. Energy is conserved, you know?
Yeah.
For things like lifting cars or braking, you need massive force over short distances.
Right, like the car lifts in garages. Shekel 13.23 shows one or hydraulic brakes in a car. You push the pedal a little way.
And that force gets multiplied enormously through the fluid to squeeze the brake pads. Or think about those powerful construction excavators, like in Shekel 13.24. Their arms use hydraulics to exert immense force. Pascal's principle is everywhere in heavy machinery.
Amazing how such a fundamental idea enables so much power. Hashtag tag outro.
Okay, let's quickly recap the big ideas from today's deep dive. Fluid pressure depends on depth and density, pushing every which way.
Buoyancy is that upward push, equal to the weight of the fluid display. Thanks, Archimedes.
And Pascal showed us how contained fluids transmit pressure perfectly, letting us multiply force with hydraulics. Yeah, it really connects ancient water systems to modern tech. These basic principles are just fundamental to how things work. And again, credit to materials like the summary we used, drawing on work by people like Hakiveli Torun for making it clear.
Absolutely. So here's something to chew on, connecting buoyancy to something massive. The source mentions isostasy, basically floating mountains or Yuzendalar. We know mountains are part of tectonic plates floating on the denser, slowly flowing mantle beneath.
Right, like giant rocky icebergs.
So if something floats, it displaces fluid equal to its weight. And apparently, only about a tenth of a percent, 0.1% of a mountain range's total volume is actually visible above the surface. Given Archimedes' principle, what does that imply about the massive unseen structure below the surface acting as a root needed to provide the buoyancy to keep those mountains stable?
That's a deep thought,
Yeah.
literally. Something to ponder.
Indeed. We'll leave you with that until next time on the deep dive.